Hello, and welcome to your first Generalized Linear Models lecture. I want to start off by reviewing the linear model. Now, all of you should be familiar with linear regression, which is probably the most common and simplest form of the linear model that you've likely heard of. Linear regression assumes that the expected value of our outcome y, conditional on the predictor values of x, is a linear combination of those predictor values. You can see in this equation at the top that we've written out this expectation is going to be equal to mu, basically the mean of the values that we expect, and it's written as a linear combination of our design matrix X, which includes all of our predictors, some of which may have been transformed in the form of dummy variables, and we combine them using the coefficients stored in the vector beta. Linear regression essentially looks like this plot. We take a straight line, or if there's multiple predictors, a straight hyperplane, and we fit it to the data. We don't assume that all of the data points are going to fall exactly on the regression line, but we do think that they'll be around the regression line with some distribution. In the case of linear regression, we're assuming that that distribution of data points around the regression line is a normal distribution, just like the one shown here. Now, linear regression makes some important assumptions. First, and something that will generalize to all of our GLMs, is that the data points are independently and identically distributed. Independent means knowing the value of one data point shouldn't help you be able to figure out any of the values of the other data points. And identically distributed actually has to do with a lot of the other assumptions we'll talk about in a second. In linear regression, we're also assuming linearity, and that also translates for all of our GLMs that we'll talk about. However, we have some clever ways of getting around linearity, so it's still technically linear, but we can get nonlinear predictions. Now, in the assumption of IID, independent and identically distributed, one of the things that linear regression assumes is that all of the errors are distributed normally. So we use a normal distribution to describe the error of different points around the regression line. Again, we don't expect that a given data point will always be on the regression line, but we think that the expected value given our predictors is going to be on the regression line with some amount of error that's normally distributed around that line. In the IID assumption, it says that they're identically distributed, which means that we automatically have this assumption of homoscedasticity, meaning that we think the variance of the errors along the regression line are going to be the same. It's not the case that we have some regions of the regression line that have very tight errors, so we're really good at predicting, and other areas where we have very wide predictions, so we have a lot of error. Now, that's what linear regression does, but how do we actually find a linear regression line or hyperplane? There's two main ways that we could talk about finding this line, and it turns out they give us the same results. The first one of those is specific to linear regression, which is least squares. The idea with least squares is kind of similar to what you may have done in a machine learning class. We have some measure of how good the model is, in this case, the squared error, so the difference between our data point and the prediction for our data point squared, and we try and minimize that. In other words, we choose the line that minimizes the squared errors. However, a more general method that we'll talk about a couple of times throughout this class is maximum likelihood estimation. Let's talk a little bit about what that means. Let's say that our job is to make a description or a model of the world, and we have some sample of data. How do we choose a description of the world that fits with that data? Well, we should probably choose a description of the world that makes that data likely to happen. Let's say that we do the world's silliest experiment and we want to find out how happy people are. So we give them a survey that ranges from -5 to +5, with 0 being completely neutral, 5 being really happy, and -5 being really unhappy. And we want a distribution, let's assume a normal distribution, that describes how happy people are. And so what we do is we go out into the quad and we find one person, get them to take the survey, and we figure out that their score on this happiness scale is 1. Now, we're really lazy, so we're not going to collect any more data. What can we do to make sure that our model of the world is accurate given what we've observed, which is that one person has a happiness score of 1? Well, let's make our problem a little bit simpler. Say these three distributions on your screen are the only three options we have for describing the world. We want to choose a distribution that makes the data we've observed, that one person with a happiness score of 1, is really likely. Because if we choose a description of the world where it's almost impossible to find someone with a happiness score of 1, that doesn't really fit well with the data that we've observed about the world. So we wouldn't want to choose that description. So let's look at our three possible descriptions of people's happiness scores. We have our gray distribution over here, our orange distribution here, and our blue distribution here. Now, what we want to ask ourselves if we're doing maximum likelihood estimation is which of these distributions makes our observation of one person having a happiness score of 1 the most likely? Well, the way we measure that is by the relative height of the distribution at the point x equals 1. I've drawn a line here, this dotted line, that shows you exactly where x equals 1. And what we can do is we can compare how tall each distribution is at that point. Now, if we compare all three, it looks like the blue distribution is the best description of the world that fits with the data that we have so far, because it has the highest likelihood compared to the other two distributions. Well, it's not impossible to get someone with a happiness score of 1 under the orange distribution. It's pretty unlikely, and it's a little more likely in the gray distribution, but is very likely in the blue distribution. So we want to choose the blue distribution as our description of the world because it makes the data we've observed likely, and all we know at this point is that data. So we want to choose a description that matches that. So in the real world, when we're doing maximum likelihood estimation for something like a linear regression, we want to choose coefficients or parameters represented by theta that make the data that we've observed pretty likely, or the most likely that we can make it. Because we're assuming with a linear regression that errors are normally distributed, we're going to have a normal likelihood function. At the top of the screen, you can see what essentially looks like a normal PDF. This is how we can determine the likelihood of a specific data point given the parameters of our linear regression stored in theta. We want to choose values of theta that maximize the likelihood of the data that we've observed. However, typically, we're going to have more than one data point. So we don't just need to consider the likelihood of a single data point, but of maybe hundreds or thousands of data points. So if for a single value of a data point, the likelihood function is given by this, then what we need to do is figure out how to combine that likelihood for a bunch of different data points. Now, earlier, we talked about the fact that one of the assumptions that we make when we do a linear regression is that all of the data are IID, independent and identically distributed. The independent part is really important here because it means that the different values of our different data points are not related. And so that means that if we want to know the likelihood of a bunch of data points, we can just multiply the likelihood of those individual data points together. And that's what you can see in the formula at the bottom of the screen. If we have a big data set, we can look at the likelihood of each individual data point, multiply them together, and get the likelihood for the data overall, given the parameters of the regression model. Remember that the higher the likelihood of our data, the more evidence we have that those particular parameters are a good fit for our data. And we want to make sure that we choose parameters of our regression model that make our data likely. So in maximum likelihood estimation, we want to choose parameters for our model, theta, that maximize the likelihood of our data. If we have a function, like the likelihood function, that we want to maximize, one of the tried and true ways that we can do that is just to take the partial derivatives of the function with respect to all of the different parameters, and then set each of those partial derivatives to 0. Remember, when our partial derivatives are 0, those are points where we expect the minima and maxima of our functions. In order to find the values of theta that maximize our equation, we can use a lot of different methods. One of the things we could do is, if it's a really simple model, we could just solve this by hand. We could directly use calculus to figure out what are the parameters of theta that make these partial derivatives 0. Or we can use some other methods that we've talked about in the past, like expectation maximization or gradient descent, that allow us to essentially do the same thing, solve for which thetas get us to or very close to 0 for the partial derivatives. Now, one thing I want to note is that mathematically, taking the derivative of a function, which is the product of a bunch of functions, can be really hard. So one of the terms that you're going to hear a lot as you get more into statistics and machine learning is the log likelihood. And it's literally exactly what it sounds like. It is the log of the likelihood function. Now remember, logs turn products into sums, and taking the derivatives of sums is a lot easier than taking the derivative of products. So we often deal with the log likelihood rather than the likelihood directly. And because taking the log of something is a monotonically increasing function, that means that any values of theta that maximize the log likelihood are also the values of theta that would maximize the likelihood itself. So that's one of the ways that we can figure out what the coefficients and the intercept, aka the parameters of our linear regression model should be. We just choose the ones that maximize the likelihood of the data that we've seen. Now, for a simple linear regression, we chose for our errors to be normally distributed. So our likelihood function for a single data point was just a normal distribution. But what if we didn't have to use a normal distribution? And this is where the generalized part of generalized linear models comes in. In a generalized linear model, no pun intended, we're going to generalize what we just learned about linear regression so that we can model a lot of other different types of variables. In a generalized linear model, there are two important things that you need to think about and choose when building your generalized linear model. The first thing is the link function. Just like in a linear regression, we're modeling the expected value of our outcome y given the different predictor variables stored in our design matrix x. That expected value is a transformation of our linear predictor, our design matrix x, times our coefficients b, and then that is put through something called a link function. Link functions are just algebra. They transform that linear prediction into a variable whose scale is actually useful to us. For instance, a linear prediction typically has a range of values from -infinity to +infinity. But what if we need mu to only be positive? Well, then maybe we could do something like take the log of our linear prediction in order to get mu so that mu is always positive. Next, we need to choose a likelihood function. A likelihood function basically tells you how data points are distributed around our expected value. Remember, our expected value is just like our typical value. We don't expect that all data points will be that value. That's just the typical or expected value. So the likelihood function tells you how our values distributed around that expected value. So keep that in mind. The two things in a generalized linear model that we can trade in and out to create different models is the link function, how we transform our linear prediction into the parameter value we want to use, and our likelihood function, which tells us how data are distributed around that expected value. Now, one of the things you might hear if you read about linear models at all is the term linear in the parameters. All this means is that we are using a linear model where our linear prediction is literally just a linear combination of the columns in our design matrix times the coefficients. So we don't actually have any nonlinearity in terms of how we're creating that linear prediction. It is literally just a linear combination of our design matrix. Now, we'll talk more about this in a couple of classes, but I do want to just give the quick caveat that it doesn't mean that our predictors themselves are linear, but it does mean that once we have all of these predictors, so all of the columns of our design matrix, we are going to be creating linear combinations of those columns in order to get our linear predictor. And I think this will make more sense as we see some of the really crazy and complicated models we're able to build with just a generalized linear model. You'll see how we can be a little bit creative with how we make our design matrix so that we're still linear in the parameters, but are able to produce complex nonlinear predictions. All right, so now that we have the basic form of a GLM down, let's talk about a model you're probably familiar with, logistic regression, within the framework of a GLM. Now, for those of you who maybe are a bit rusty, logistic regression is a classification model, meaning what we're trying to predict is actually a category. Let's say that we're trying to predict whether someone is or isn't registered to vote, or whether someone has a dog or doesn't have a dog. Now, because what we're trying to predict is a category, what we end up wanting as the output of our model is a predicted probability. That can then help us bin people into likely to be registered to vote or likely to not be registered to vote. But probabilities are not continuous in the sense that they can't have a range of values between negative infinity and positive infinity. Rather, they're bounded between 0 and 1. And so we need a link function that can get us from a linear prediction, our x times beta, to something like a probability that's bounded between 0 and 1. So in order to choose our link function, we are going to need something that can make that transformation. And in this case, what we're going to use is the logit link function. The logit link function will take in our linear predictor x, and it will give us something that is bounded between 0 and 1. In other words, our predicted probability. For some weird reason, we actually call the link function the function that undoes that transformation, the function that can actually take our probabilities and transform them back to the linear predictor. And then the inverse of the link function is what we actually apply to those linear predictors. I don't like the terminology, but that's how people refer to it, so it can be important to just keep in the back of your head. Now that we've chosen a link function that transforms our linear predictor, we need to choose a likelihood. Remember, the likelihood tells us how our variables distributed around our expected value. Now, because we have a categorical prediction, and let's assume it's a binary, so a 0 or 1 categorical prediction, we need a distribution that can handle binary variables. And one really good one is a Bernoulli distribution. So we are going to pair our logit link function with a Bernoulli likelihood. This means that for a given predicted probability, we expect that the data are Bernoulli distributed. So if we have a predicted probability of 80%, it doesn't mean that all of the data points are always going to be a positive, but it does mean that we think they'll be distributed as a Bernoulli random variable with a predicted probability of 80%. And just like with a linear regression model, we can use maximum likelihood estimation to figure out what the parameters, so the intercept and coefficients of a logistic regression should be. And when we use maximum likelihood estimation, we're of course going to swap out the distribution that defines our likelihood function. With linear regression, we assumed a normal likelihood, so we use the normal distribution as our likelihood function. However, now we're assuming that our errors are Bernoulli distributed. So as you can see in the formula at the top, this allows us to use a Bernoulli distribution as our likelihood function. Now in class, we'll talk about a wide range of GLMs that you can use by just swapping in and out some of the likelihood functions or link functions. However, one of the things that I want you to think about is how you might choose these. For a link function, you need to think about what range of values can mu, your expected value of the data, take on. In linear regression, mu can be any value between negative infinity and positive infinity. So we actually use something called the identity link, which is nothing. It's literally saying that the link function is just return the variable as is. However, in a logistic regression, our expected value is a probability, and so it has to be bounded between 0 and 1. So we can't use the identity link, at least we usually shouldn't. So instead, we choose a link function that transforms our variables in order to get that expected value we want. We take our linear prediction, which is always going to be between negative infinity and positive infinity, and we transform it using the logit link in order to get a value that is now bounded between 0 and 1. So when choosing a link function, you need to think, what values or what range of values can my expected value take on? And what link function could take me from my linear prediction to those range of values? Now, when you choose a link function, I want you to remember that this is going to change the interpretation of the coefficients from your GLM. When we fit a GLM, the coefficients are always going to be in terms of that linear prediction. How does an increase of 1 unit of a predictor change the linear prediction of our model? However, usually we don't care about that linear prediction scale. We want something called the response scale, which is the scale that our expected values are on. And so I just want you to keep in mind that depending on the link function you use, the interpretation of your coefficients might be a little bit different. And last but not least, let's talk about the things you need to consider when choosing a likelihood function. With a link function, we need to think about the range of our expected values. With a likelihood function, we need to think about the errors of our actual data and how they're distributed. For a linear regression, values are continuous, and we assume that they're distributed normally. For logistic regression, values are binary, and we're assuming that they're distributed in a Bernoulli distribution. Now, these aren't the only distributions that work. We'll talk about a couple of more in class, but when choosing that likelihood function, you have to consider what are the actual units of our outcome variable, and how do we think they're distributed in terms of error around the expected value. All right, that's all I have for you. I will see you next time.